everyone. Good morning, good noon, maybe good afternoon, or good evening for someone. So the topic for this seminar is integrating microstructure analysis in geothermal geomechanics, mechanistic insights into thermal damage and hydraulic fracture dynamics. So that is title for this talk. I will not say anything details for this talk, but let me say a few words for the to introduce Dr. Kumari. So she is a lecturer in geotechnical engineering at the School of Civil Mining and Environmental and Architecture Engineering of the University of Wollongong, Australia. So she received her PhD from Monash University and also in Australia, with a focus on geomechanics applications for deep geothermal extractions and hot dry rock reservoir simulation. So she is a recipient of the 2024 Discovery Early Career Research Award from the Australian Research Council. So which supports her current research focus on investigating heat recovery and energy storage from underground mines. So that's a brief introduction to Dr. Kumari. You can start. Yeah.
Thank you, Meg, for your introduction. I'm going to share my screen. Okay. Can you all see my screen?
Yeah.
Okay.
So by the way, before you start, how do you want other people to ask your question? Do you want everyone put a question on the chart, or they can ask whenever they have a question?
Shall we ask all the questions at the end?
Okay, let's for the audience, let's ask question at the end, or you can put your question in the chart. Okay,
in the
thanks.
chat. Yeah, thank you. Yeah, thank you very much for this opportunity. And thank you very much for accommodating the time difference and scheduling this in a bit convenient time for me. So today I will be presenting about some of microstructure analysis I could involve in geothermal geomechanics domain, particularly thermal damage and hydraulic fracture dynamics. So in this presentation, I will give a quick overview to Australia's geothermal resources and potential and importance of conducting research in this area. Next, I will talk about some selected topics as examples to go through importance of microstructural analysis in this research space. Before moving to the presentation, I thought to briefly introduce my background as well. I received my bachelor's degree at the University of Ruhuna, Sri Lanka, and as Ming also already explained, received my PhD from Monash University, which is located in Melbourne under the supervision of Professor Ranjit Pathegama. And during that period, I mainly looked at research related to deep geothermal energy systems in Australia, particularly for dry rock energy systems. Then I worked as a postdoc there before joining Wollongong as a lecturer. Wollongong is a beautiful coastal city situated south of Sydney. And I received a prestigious Australian Research Council Discovery Early Career Research, which support my current research focus. I want to acknowledge the research training and experience I received from Professor Pathegama's Geomechanics for Geoenergy and Georesources Deep Research Group, or 3G Deep Research Group, and his mentorship. That's why I thought to put this slide. 3G Deep Research Group aims to contribute to challenges of deep earth mineral and energy resources. The intention is to better represent actual field conditions like realistic in situ stresses, temperatures, discontinuity pathways, fluid flow, etc. And we have developed a variety of custom built large-scale testing devices, as well as facilities for microscale observations. And we also collaborate with various other institutes to enhance these capabilities. So as the title highlights in this talk, I will go through how microstructural analysis can be beneficial for geothermal applications such as thermal damage and hydraulic fracture. As a researcher exploring geothermal geomechanics research, this talk will be incomplete if I do not talk a bit about why this research area is important in Australian context. In Australia, we can identify 3 geothermal resource categories, as you can see here, considering the depth, which is an indication of approximated temperature and the amount of enhancement required to produce flow rates. So shallow direct use geothermal resources are typically located in between 0.5 to 1.5 kilometer depth range. These are mostly aquifers with high permeabilities at low to moderate temperatures and useful for direct use applications. Deep natural reservoirs are resources that are typically greater than 1.5 kilometer depth, and they are generally sedimentary or fractured aquifers with high natural permeabilities, and they can be useful for both direct use or electricity generation. Deep crystalline formations, they are also called as hot dry rock reservoirs, require significant permeability enhancement by engineering means. That's why they are also called enhanced geothermal systems. And mainly the application would be electricity generation in this kind of formations. And this shows various current and planned location for geothermal exploration in Australia at the moment. This slide summarizes how Australian geothermal resources could potentially be utilized depending on the depth as well as temperature ranges. As I mentioned earlier, crystalline rock-based hot dry rocks or hot sedimentary aquifers are the target reservoirs for geothermal-based electricity. We need significant reservoir stimulations because we do not have volcanic-based geothermal systems like in New Zealand. And considering the Australian context, there are extensive, particularly in the central Australia, where temperature has estimated to reach at least 200 degrees, around 5 kilometer depth. And several companies have attempted to explore these geothermal resources in last 2 decades and had variable success. Shallow geothermal technologies such as ground source heat exchangers accompanied by heat pumps for heating and cooling applications are gaining popularity in recent years. Another type of potential geothermal resource currently we are exploring is mine-based geothermal systems. There are deep underground mines in Australia that have reached temperatures beyond 40 degrees Celsius in some instances, and cooling of active mines are challenged as well. And we also have a lot of historic legacy kind of mines. The hydraulic conductivity of these systems are quite high when they are flooded because of artificial voids like mine galleries, shafts, fractured and porous rock, etc. Therefore, we can expect a very high water yield. And my current Australian Research Council project aims to identify these kind of potential sites and discover various methodologies to make them usable. Next, I would like to briefly talk about geomechanics research needs for geothermal harvesting. When it comes to geothermal energy, geomechanics provide essential fundamental inputs into many areas. Primarily, it's important to understand the properties of subsurface rocks, their ability to store and transmit heat, which we identify as reservoir characterization. It's crucial to understand the stresses and strains within the earth crust, which affect reservoir stability as well as fracture propagation direction. As I mentioned earlier, when permeability is not sufficiently high, it is important to create fractures artificially, and it's also important to ensure integrity of geothermal wells, preventing leakages, maintaining long-term fluid transport, thermal recovery, etc. So essentially, the knowledge of coupled thermo, hydro, mechanical, and chemical mechanisms is needed to understand these systems, and it's a very complex problem. So this sketch summarizes how these processes are interrelated. For example, temperature, pressure, and chemical effects will alter fluid and rock properties. Temperature and pressure can also alter hydraulic and chemical processes, such as changes in fracture pathways, mineral dissolution, precipitation, etc. So multiphysics coupling techniques are used to uncover some of the challenges. However, simulations can be computationally intensive and require significant computational resources. And these models often require validation, and which may require advanced experiments, which can be quite challenging to design and perform. Another important aspect I would like to highlight is the need to consider the scale effect for these processes, coupled processes. We often conduct small-scale laboratory experiments to understand the complex reservoir processes. There is no question microscale observations, for example, porosity, pore network, rock fragmentation, tortuosity, influid flow, leaching, chemical processes, they are very important to understand the underlying complex mechanisms. And this proposed framework shows various techniques that can be used to capture these physics and develop constitutive equations and apply this knowledge to understand these coupled processes and interactions and continue that knowledge to field scale. And this four-stage modeling can capture this whole process from microscale to reservoir scale. And this could be useful when we are continuing this research area. When it comes to experimental geothermal geomechanics, often researchers require to design and develop unique experimental systems to simulate deep underground conditions. Therefore, first, I will briefly introduce some unique experimental facilities I could utilize for this research work that can simulate in situ stress temperature conditions applicable to geothermal environment. Next, I will introduce some experimental work as well as modeling that we conducted to understand the influence of heating, cooling on reservoir rock under in situ stresses, as well as laboratory scale hydraulic fracturing with various fracturing fluids and permeability of reservoir rocks. This is a unique solution developed at 3G Deep Laboratory for geomechanics testing for high pressure and high temperature environments. So we extensively utilize this system to understand the mechanical behavior of rocks, hydraulic fracturing using water, as well as other different fluids like CO2, foam, and to understand flow behavior of rocks. And this is how it looks like when we disassemble this system. And some of the unique features of this system are the extensive operational range. We can have confining pressures up to 150 megapascal, temperatures up to 350 degrees. So the idea is to simulate up to 5-kilometer depths, targeting dry rock reservoirs in Australia. We can inject various fluids, water, CO2, etc., up to 165 megapascal to simulate hydraulic fracturing. To achieve these extreme conditions, we have these custom-built syringe pumps, and we have employed various unique fluid sealing solutions. And we can measure temperature, pressure, displacements, fluid flow rates, using various sensors and thermocouples. Next, I would like to briefly go through some of the research studies that I conducted. Here, thermomechanical behavior of granite rocks. Thermomechanical behavior of reservoir rocks is influenced by various factors like type of rock, mineral composition, porosity, pre-existing fractures, environmental conditions like temperature, stress, fluid saturation, etc. And this is some early work I conducted to understand the combined effect of both temperature and in situ stress. In our experiments, we used various Australian granite types targeting, again, hot dry rock applications. We know traditionally rock failure in compression can occur in two main ways: dilatancy and failure by strain softening under relatively low confining pressures, and failure by strain hardening under elevated confining pressures. So this has some experimental evidences showing how rock failure alter with extreme confining pressures with the transitional regime at intermediate pressures. We observed when specimens fail below 60 megapascal confining pressure, they mainly fail by shear localization. However, when samples tested beyond 90 megapascal, they exhibited some strain hardening characteristics. The effect of temperature was another important aspect we considered. Based on these results, we observed temperature cause a strength reduction after certain temperature. For example, in this selected granite type, the temperature dependent strength reduction was initiated beyond 200 degrees. So this temperature threshold value is actually material dependent and stress dependent. We also attempted to model these scenarios, and this is an attempt to develop a nonlinear failure criteria using temperature-dependent material properties. Geothermal reservoir rocks are often subjected to large temperature gradients as a result of rapid heating or cooling. So traditionally, we use water as fracturing and heat carrying fluid in geothermal systems. And during the injection of cold water into the hot rock around the borehole, rock is subjected to sudden temperature changes, resulting in generation of thermal stresses. However, with increasing the distance from the borehole, the corresponding cooling rates will change. So to simulate these different thermal conditions, we considered different scenarios. Continuous heating without applying any cooling, and then rapid cooling by quenching heated samples in water to mimic fluid circulation, and applying slow cooling or allowing sample to cool down on a desired rate to replicate the natural cooling of surrounding rock. We also used a non-contact optical 3D deformation measuring system to understand axial and lateral deformations in these kind of experiments. In general, as a result of thermal stress, granite's compressive strength and elastic modulus will nonlinearly decrease, while axial strain and Poisson's ratio are increased as a result of thermal-induced damage. Researchers have observed a significant increment in thermal-induced crack density generally after 600 degrees. The main reason for this is suggested as the alpha to beta transition of quartz, which occurs at 573 degrees. Here, they considered the specific granite called Strathbogie granite, consists of large amount of quartz, about 50% of its mass, which is the primary constituent of this thermally induced damage. This study shows thermomechanical response of granite subjected to various thermal cyclic conditions, like continuous heating followed by quenching and applying that sort of thermal cycles multiple times, focusing on evolution of failure mechanism under these thermal loads. So below 300 degrees, we observed the failure is predominantly shear dominated, exhibiting relatively simpler fracture planes. However, as temperature exceeds beyond 300 degrees, the complexity of failure planes increased, especially beyond 500 degrees with multiple thermal cycles, and beyond 600 degrees, this mechanism was quite complex. In the right-hand side, you can see the effect of temperature on cyclic quenching on mechanical properties like strength, modulus, axial strain at failure, Poisson's ratio, shear modulus, as well as brittleness index. So these kind of parameters are quite important for the further modeling aspects. Overall result shows thermal cycling induced significant microstructural damage, weakening rock's overall strength and stiffness, and also making it more prone to deformation and failure under stress. We also used acoustic emission detection technology to study crack propagation processes in granite under high temperature conditions during shearing. We know that when a brittle material is under stress, strain energy is released during the development of new cracks or widening of existing cracks. And we can capture this energy release using an acoustic emission system. Researchers have divided crack formation into different stages. For example, crack closure, crack initiation, secondary cracking, crack damage, etc. Considering the experimental observations of cumulative acoustic energy plots, here we identified 3 different stages. Initial crack closure, when most pre-existing cracks are first closed, there is a insignificant release of AE counts, and then stable crack propagation period where release of AE energy gradually more linearly, and then unstable crack propagation period where exponential increase in AE energy, and then damage or failure. We also studied post-failure aspects, but I did include this particular results doesn't capture that aspect. We defined then this stress threshold ratios combining stress strain curves and cumulative AE counts, as you can see in these plots. AE analysis further confirmed this thermal induced damage upon heating followed by cooling. With increasing temperature, we observed both elastic region as well as a stable crack propagation region of granite decreases, with the increase in unstable crack propagation region showcasing the rapid damage. And also cooling of heated samples in a rapid manner further accelerated these mechanisms. Acoustic emission technology was further employed to understand the crack propagation process during cyclic heating and quenching. And the data again indicated decrease in the stable crack propagation region, and alongside increase in unstable crack propagation region with increase of number of quenching cycles, suggesting transition towards more thermally damaged state as crack density intensified. When it comes to quantifying thermal damage, we use temperature-dependent Young's modulus as well as uniaxial compressive strength as indicators, and up to 600 degrees, we found quite a linear relationship between temperature and thermal damage. However, beyond 600 degrees, there was a shift to a nonlinear regime, highlighting the importance of more advanced models to capture this damage evaluation at extreme temperatures. Given today's focus is on integrating microstructural analysis in geothermal geomechanics, next I will move into microcracking mechanisms triggered by thermal loading. Among advanced microscale techniques, computed tomography or CT imaging has evolved to quantify pores and microfractures, providing digitization of internal structure. When CT resolution, like this is a CT image, is not sufficient, scanning electron microscopy or SEM can be used, but this may require sample stitching and then image analysis for quantitative analysis. First, I want to acknowledge Australian Synchrotron and Monash Centre of Electron Microscopy for their support in accessing these facilities. By examining micro-CT and SEM images of thermally treated granite at various temperatures, we observed substantial matrix degradation in reservoir rocks caused by thermally induced microcracking. In crystalline rocks like granite, we can identify two major modes of cracking. Intergranular cracking, this means cracks propagate along grain boundaries, as well as intragranular cracking, where cracks occur within weaker mineral phases. The results show that propagation of cracks through grain boundaries significantly increase with the increase in preheating temperatures. Increasing temperature further creates thermal stresses in the rock mass due to its natural anisotropic nature, because rock mass consists of different minerals and they have different thermal expansion coefficients and thermoelastic moduli. Once thermal stress exceeds the internal strength of rock matrix, fractures are initiated through pre-existing grain boundaries along large grains. We studied damage mechanism of different granite types. For example, quartz mineral was the most abundant mineral for the Strathbogie granite, and it showcased relatively higher thermal induced damage compared to Harcourt granite, which was predominantly a plagioclase and felspar dominated granite. Here you can see some of the selected high resolution 2D CT images showcasing thermal damage associated with slow cooling and here rapid cooling. And this is the algorithm we use to post-process CT data for quantitative analysis. We started with 2D raw images with a resolution around 10 micrometers. Then we use noise reduction medium filter that preserves key image features. And then after filtering, we use unsharp masking to enhance mineral boundaries and edges. We identified minerals and cracks by examining contrast and brightness in the micro-CT images where density affected intensity values. Then multi-thresholding segmentation technique was used to separate individual minerals and pores, providing detailed view of the rock microstructure. I will talk about the steps of constructing the 3D structure employing 2D images and pore network modeling in the coming slides. Crack quantification involves determining total and connected porosity. Total porosity was obtained through segmentation of 2D images into cracks and minerals and removing isolated pores to calculate connected porosity. These are the plots that shows distribution of total porosity, connected porosity over the height of the specimen. And these are the plots showing total and connected porosity over the diameter of the specimens at different heating and cooling conditions. We observed the heterogeneity in the porosity distribution, as you can see here, especially below 600 degrees. And we quantified this effect using a heterogeneity coefficient as well. And one thing we observed is a significant reduction in heterogeneity in microcracking with the increased temperature beyond 600 degrees. Here you can see the average porosity plots for different temperatures and cooling conditions. Overall, as expected, we observed rapid cooling of heated rock specimen generated connected microcracks in the granite. Next, we generated pore network models to understand the size and distribution of pores inside the granite microstructure. The pore network generation is a systematic process. This begins by simplifying the structure to identify the shortest path between empty spaces and the surrounding material. Next, we partition the network by identifying key connections, separating them from the larger pore space and isolating individual parts of the structure. Finally, we can create a model that represents the interconnected pore and throat spaces using visual elements to show size differences in these components. Pore network models provide detailed information such as pore and throat radii, their coordination numbers, lengths, areas, and volumes, offering insights into structure and function of pore network in fluid and heat transport studies, which I will briefly explain in the coming slides. So these are the created pore network models for thermally treated granite specimens. And you can see the complexity of pore network increase with increasing temperature. And also more complex dense pore network is seen in rock specimens subjected to quenching or rapid cooling compared to the slow cooling situation. And these are the results for granite subjected to cyclic quenching treatments. So you can see the temperature and number of cycles. We could not generate pore network for 500 degrees at one quenching cycle for this considered resolution. However, after multiple quenching cycles, pore networks began to form due to this interconnected fractures. Increasing quenching cycles resulted in a substantial rise in pore and throat counts, especially larger pores appearing near the sample boundaries or edges and small pores expanding internally. Here you can see further analysis conducted based on the pore network model. So this plot shows the equivalent radius of pores and throats, providing valuable insights into size distribution within pore network model. Based on the results, you can see here 500 degrees, 5 quenching cycles. The pore radius is ranging up to almost 1,500 micrometers, and it has been increased almost 2,000 micrometers with 15 quenching cycles. And you can see variation with various temperatures and quenching cycles. And pore throat radii also increases corresponding to the thermal damage, as you can see here. Data also suggests that quenching cycles can have significant, particularly more impact than temperature alone in these observed conditions. So repetitive thermal cycling amplifies microcrack propagation and pore expansion more effectively than a single high temperature exposure. The coordination number in the context of pore network models refers to the number of throats connecting to a single pore. A higher coordination number indicates that pore is connected to many throats, which enhances fluid connectivity and improves pathways for transport, making the system more permeable. However, in some cases, such as during extreme thermal shocks or repeated quenching, cracks can merge into larger pores, reducing the number of throats and potentially lowering the coordination number. Therefore, we can understand that coordination number provides a quantitative measure of the evolving complexity and connectivity of the porous network within the rock. Next important parameter is the channel length, the distance between two neighboring pores. The channel length generally decreased as thermal conditions intensify, as you can see in these results. The decline in throat length shows the formation of larger pores due to crack propagation and thermal expansion, which reduces the overall channel length within the rock's porous network. The permeability is another important aspect. The permeability of granite samples was then simulated using a pore network model, focusing on fluid flow streamlines between connected pores. The results show that temperature and quenching cycles significantly impact the permeability values because of formation of well-connected pore network, which facilitates fluid flow, leading streamlines and high-velocity regions. The permeability obtained from simulations shows increase with temperature and quenching cycles. For example, permeability was 7.6 Darcy with 500 degrees 5 quenching cycle, and it has increased to 12.4 Darcy with 15 quenching cycles, and you can see effect of both temperature and quenching cycles in the figure. The enhanced permeability shows that development of connected fracture network within granite with higher temperatures and quenching cycles promoting greater interconnectedness of pores and cracks, facilitating fluid flow. We also try to verify these results by conducting laboratory experiments as well. And here you can see results of laboratory tests as well. Here you can only see one sample treated at 600 degrees at one quenching cycle. We found steady state flow rate is linearly increasing with pressure gradient for all confining pressures. We studied up to 40 megapascal in this situation. And we kept injection pressure less than confining pressure to avoid hydraulic cracking in this kind of experiments. And these are the calculated permeability values, and results showed nonlinear reduction of absolute permeability with increasing confining pressure. Here, the simulated pore network modeling was performed under atmospheric conditions because we didn't perform any CT work under pressure. And then we tried to compare permeability values of the simulations as well as experimental results under same confining conditions, and found the results are within the same order of magnitude. Next, I would like to move to the
Hi.
next.
Sorry, Dr. Kumari. So how many slides we have?
I will finish in 10 minutes.
Yeah, we need to make sure we have like 15 or 10 minutes of question section. It's we only have 17 minutes left.
Okay, I'll try to finish this quickly. Thank you.
Yeah. Okay.
Okay, next, this is the next component of the talk, hydraulic fracturing of granite rocks at geothermal conditions. In this test, we considered cylindrical rock samples, and we control the stress state to make sure we have a vertical fracture along the well bore, and we created the well bore using a 3 millimeter drill bit. And here you can see the generated breakdown pressure curves, and we studied how breakdown pressure evolves with confining pressure and temperature. We use various fracturing fluids such as water, carbon dioxide, and at the moment we are using foam, and we are working on improving foam stability by adding various surfactants, nanoparticles, polymers, etc. And when it comes to CO2-based fracking, phase transition is an important element. Therefore, we are controlling temperature and pressure and monitor rheological parameters like viscosity, compressibility in this kind of simulations. And this plot shows well bore pressurization curves of different fracturing fluids and their impact. important thing I want to highlight is fracturing fluid, in situ stress, temperature. They have an important effect on fracture propagation and development of secondary cracks, which we further studied using CT technology. So these are some micro-scale features induced by water-based cracking, and this result shows fractures tend to propagate along grain boundaries mainly. However, when propagation continues, they tend to break weak minerals, usually large grains, minerals with pre-existing microcracks, forming intergranular cracks in some situations. Under confining pressure, there could be closure of the fracture due to grain crushing, and we also observed very small thermally induced cracks close to the well-bore zone with injection of hot water into the injection of cold water into the hot rock. These are some examples of microstructure of CO2 fractured granite, and we can see tensile fractures induced at the well-bore, and we observed diametrical fractures with secondary branches under high confining pressures with CO2 fracturing. These images shows the effect of temperature. One thing we observed is at high temperatures like 200, 300 degrees, fracture do not propagate along the full length of the rock specimen. Instead, the microfractures were directed into the circumferential periphery of the rock specimen. This caused leakage of CO2 into membrane along the fluid flow paths made from the microcracks. We could confirm this phenomena by observing outlet pressure where we observed a gradual surcharge. And we found temperature significantly affect the morphology of induced fractures. Here you can see how fracture tortuosity increases with temperature and how average fracture density changes. We observed at high temperature, CO2 has potential to percolate into thermally induced microcracks, forming new cracks or propagating existing fractures. And compared to water-based fracturing, CO2 produce complex fracture networks with multiple fractures and connections. These microstructural observations helps to explain the flow characteristics of induced fractures under high pressure, high temperature environment. This result shows the effect of confining pressure. These CO2-induced fractures are very stress sensitive, and you can see a significant nonlinear permeability reduction with increasing confining pressure. Another finding is permeability of CO2-induced fractures are more than 3 orders higher that of water-induced fractures, which is analogous to morphology identified by CT analysis. This is the last work I'm going to present, a coupled hydromechanical distributed element model that simulated hydraulic fracturing on crystalline rock at grain scale. This was produced using 3D software. The permeability of grain assembly was matched to the intact granite matrix permeability by making grains impermeable, allowing fluid flow only between grain contact. And we mimicked hydraulic simulation on intact grain assembly by considering compatible injection flow rates. Here you can see modeled contacts between grains using a Coulomb slip model, allowing contacts to fail under both shear and tension. And here left, you can see CT scanned granite sample as well as simulated microstructure and numerical and experimental breakdown curves. Here you can see simulation results on fracture behavior and stress influence, and also the effect of stress anisotropy. At stress ratio 1, fracture grew diagonally, influenced by grain arrangement, and with increased in situ stresses, it led to additional microcracking and a greater tortuosity of the main fracture. And Another observation was hydraulic fractures are highly sensitive to stress anisotropy at stress ratio 2. The fracture grew in the Y direction with minor crack branching, but branching was suppressed as stress ratio increased to 5. Also, low tensile to shear crack ratio was observed in this case 4 with a strong impact of stress anisotropy. These are some results showing the impact of grain arrangement and grain contact on fracture propagation. Results show that despite maintaining the same injection rate and in situ conditions, grain arrangement influenced both fracture path and fluid leak off into the rock matrix in these simulations. Considering the time limit, I conclude my presentation here. Today, I presented some selected research relevant to thermal damage and fluid-induced fractures with special reference to microstructural analysis. Overall, thermally induced microcracking and pore expansion play an important role in damaging rocks in geothermal environments, affecting fluid flow and fracture. So choice of fracturing fluid like water, CO2 foam can also impact how fractures form, with foam and CO2 offering benefits in reducing water use and creating more complex fracture networks. And I want to thank for your attention. This material I presented is a collaborative research effort. Therefore, I want to thank my PhD supervisor, Professor Pathegama, all my mentors, colleagues, my students, collaborators, and thank you for the support from Monash University and University of Wollongong, and thank you for this opportunity.
Okay, great. Yeah, that's very impressive presentation and a lot of work. So yeah. So any question from the audience? So yes, I personally pretty familiar with 3G deep because when I was like trying to apply in my PhD, I applied there, but didn't got.
Okay.
Yeah, but so yeah, I'm familiar with most of the techniques of experimental facility like yeah, doing here. And I know someone, like some Chinese students who graduated from there. Yeah, some of them went back to China, someone went to somewhere else. So let me ask one question. So when you talk about that you have quenching for the
Yes.
rock, and then in my understanding, what you did is you actually use some kind of oven or another device to like to heating the sample and then cooling it. And then you use your triaxial facility to measure its properties. Am I correct?
Yes, that's correct, because our triaxial facility can heat only up to 350 degrees.
Yeah.
So
Yeah.
if you want that target temperature, then you can inject cold fluids. But if
Okay.
you want to heat beyond that, we used a different oven, and then we applied water quenching.
Okay, yeah, that makes sense. Then the following question for that is like you mentioned that for the enhanced geothermal formation system or like a geothermal reservoir like 5,000 meter depths, the temperature is below or around 300 degrees C. So my question is like, what's the motivation for studying those quenching effect? Like you increase to more than 500 degrees C or even 800 degrees C, and then you cooling it down. So my question is, why is the we care about this phenomena? How can this happen in the field?
That's a very good question. We actually studied a lot of work with stress and temperature under low temperatures. That's why triaxial system is obviously designed to 350 degrees.
Yeah.
But when it comes to microstructural analysis, the resolution is not sufficient to capture all the thermally induced fracture networks. So in order to do this study continuously, we kept on increasing the temperature so we can have a better understanding of this microstructure. But these could be useful for other different applications like fire, etc. Still, I think results are useful.
Okay. Yes, thanks. And another question, like in the US, it's the same thing. Like um, yeah, we are care about we are moving towards from oil and gas to geothermal, and also some other types of renewable energy. So for geothermal, they also talk about the super hot rocks. So that the temperature goes like above 300 or 350 degrees C. But from the data, you show your slides, it seems like if the temperature is below 400 degrees C, it seems there's no big difference for the granite properties. Like if you compare like 100 degrees C or 400 degrees C, am I understanding it correctly?
Yeah, that's correct for this considered granite, but this could be different for other different types of rocks. But we
Yeah.
observed for many rocks thermal degradation, the thermal induced damage or the interconnected traction networks appear beyond maybe 500, 600 degrees.
Yeah. So my question, like, from your experience or the past experimental work done at 3G deep, what types of rock has like a critical boundary, like maybe around or even below 300 degrees C?
I have a slide showing some data from Australian
Okay.
various rocks, both sedimentary rocks and igneous rocks. So let me share that
Okay.
work.
Okay.
So this slide shows, can you see,
Yeah.
the
Yes.
change of normalized compressive strength, which means they have normalized temperature dependent compressive strength with compressive strength at room temperature.
Yeah.
And when it comes to sedimentary rocks like sandstone, mudstone, the reduction even happened beyond 600 degrees. There's not much difference, but this can vary depending on type to type. But granites showed quite consistent behavior in these experiments. But we need to do laboratory scale experiments to understand this behavior when you change the material.
Yeah, from this one, from the upper right one, it shows that if after more than 200 degrees C, you will see the strength decrease for granite. Okay.
Yes.
Okay. Hmm. Okay, and then can you go back to your slides 11? Oh, but by the way, anyone in the team has any questions? Okay. Yeah, that's why we'll continue to ask. Yeah, can you go back to the slide 11?
Yes.
Okay, thanks. Sorry, 12. Next one.
Yes.
Yeah. So for this one, you can say you measure so I assume for this test, it is measured under high pressure, high temperature inside the traction cell, right?
Yes, that's correct.
Okay,
There's
so
no cooling.
okay, I see. So basically you um um heat the assembly, the whole setup to 300 degrees C, and also increase the confining pressure to, for example, 50 or 100 MPa, and then you start to compress break the rock.
Yes, that's correct.
Oh, okay, and then for this specific rock, you can say if we compare the stiffness between 100 degrees C and 300 degrees C, the results are very similar. So it makes me thinking for this specific granite, the temperature, if temperature is below 300 degrees C, the strength is not that big difference.
Yes, I can agree with you because you can
Yeah,
see
okay.
the 100 degrees curve and then 300 degrees even higher. Strength was even higher compared to 100 degrees.
Yeah, it's very but not that big difference, right? Is that a big difference?
No, I don't say it's maybe
Oh,
maybe
okay.
10%, but we need to take into
Yeah.
account the heterogeneity of the sample as well.
Yeah, what's more interesting, like you say, for that room temperature, it's even it's closer to 100, and then for 200, it's become as highest, and then for
Yes,
300, you come back, and then the 300 is pretty close to that room temperature curve. So it just makes me
yes,
wonder, is it really necessary to do the like a 300 degrees C compressive stress test? But I'm not saying like I'm not asking you. I'm just thinking for my for our laboratory, for our work, because we are right now considering building another tracer cell. Right now, we limit our cell to 200 degrees C, and we want to increase to 400 degrees C. But for these results, I'm just wondering, is it really necessary or not? Because just in terms of strength, there is not big difference.
I think you can gain a lot of insights from the uniaxial compressive strength. That's first thing you can do to understand the behavior. So you can easily do this kind of experiments.
Yes.
So in the UCS condition, you can see there's a strength gain until 300 degrees, but always we observe strength reduction beyond 400 for this granite type.
Okay.
But if you use rapid cooling, then there was continuous decrease because of the thermal shock you apply.
Okay. Yes. Thank you. That's all my questions. Yeah. Very impressive work. Yeah.
Thank you very much.
A lot of publications. Yeah. So any other questions from the audience? Oh, okay. Great. Okay. Thank you, Dr. Kumari. So, thank you for giving us this great talk. So, yeah, let's keep contact. Let's keep in touch in the future. Yeah.
Thank you.
Thank you. Have a nice
Bye.
weekend.
Yeah.
Bye.
Bye.